optimization application demos, what they are. And so these are live, brand new from Gurobi, live web-based demonstrations of optimization problems using Gurobi. We have two so far. One is the cutting stock demo that you'll see today. And time permitting, we might also show the workforce assignment demonstration, application demo, I should say, that is the other one. And that's shown at the right here on the screen. So you can see that that's for a workforce assignment problem. These are always going to be problem specific. But their purpose, especially these first two, is to demonstrate Gurobi for operations researchers and other audiences. We think operations researchers will find these first two fairly simple demos interesting because they're going to show how to architect an application like this. And so we're trying to keep these first two very simple, and in order to demonstrate architecture and some other basic functionality that's really not an OR subject. But we know a lot of operations research professionals are interested in doing this with their models, getting them, making them more usable to the audience that they're trying to serve, and also maybe more performant. So we think that'll be interesting for OR people. But we think also data scientists will find these useful because they give context. A lot of people who are new to optimization need the context to understand the problem they're solving before they dive into the modeling. Most of us in the Gurobi world are used to bringing up a text editor and looking at a model, and that's a rich universe to us. And to a data scientist, that's not an alien thing, but giving context to that is a very useful thing. For business people, though, it's critical to have a user interface. We find it's really hard for a non-OR, non-data scientist type of person to understand what's going on. Just looking at a model doesn't do it. So a user interface is critical for demonstration purposes. Obviously, it's even more critical for usability purposes when deployed. And then also, we think the architecture we're proposing here is going to be useful to IT as kind of a blueprint. And you'll see more about that as we go forward. So these are proof of concept optimization applications, usable by non-OR people, but we think OR people can use them to demonstrate concepts to others. So that's the general purpose of these things. But we also want to be clear about what these are not. Okay, so these are not part of the Gurobi solver. The solver is still focused on solving optimization problems very fast, very quickly, and robustly. And that's not going to change. So these are not a Gurobi product. They're not something we intend to sell to you. These are free demos. And also, though, that makes it possible for us to release them as source code. For now, they can be made available to you on request. We might do something a little more accessible later, but right now, if you request them, we'll be able to provide the source code to you. And the idea is that you replace the parts you don't like or that you see fit to replace with other pieces of a similar kind, or just maybe just use one part and forget the rest. And I can talk about those two scenarios as we go through the architectural discussion today. So I think that'll be useful to you. Now, I didn't develop these. I'm the talking head, so to speak, today. The development team for these demos was led by Michel Jasinski. He's the lead architect. Olivier Noiret was the user interface developer. Fernando Orozco did the backend architect and development. Juan Orozco was a modeler and developer on the project. And then Pano Santos was the lead modeler. And the key point here, these people are not just strictly OR professionals with no real world experience. They do have real world experience, and that's the reason they're on this team. And so this project is intended to be real world. It's not an idealized notion of how an application could exist. It could actually be used by you on your own models to deploy to a real world audience of users. A cutting stock problem is a kind of a classic OR optimization problem. But some of you, just in case we're not all on the same page, I'll give a description of it. For the OR people, they've been through this before, so you can have a sip of coffee and I'll get through this quickly. Then we'll see the demo. So the machine that you see in the screenshot is used to cut master rolls of material. And now we see, looks like paper in this one, but it could be aluminum or steel or fabric, any kind of rolled or it doesn't even have to be rolled, it can be pipe, any kind of material that comes in master sizes and that needs cutting down. And so in a lot of factories, they have production lines that need small rolls of particular sizes. And so for this purpose, for this demonstration, we're assuming that the operator has a set of demands for each production line. This production line wants a 15-inch width roll, and they need 11 of them. And for this simple example, we're only considering one time period. A real-world example would consider multiple time periods into the future, but this is a single time period. Because again, for this sample, we're trying to keep it simple to demonstrate architecture and also to introduce people to modeling if they're new to math programming. So this is as far as optimization goes, a fairly simple demo. Architecturally, though, I think you'll find it interesting. Right. So so I said we have master rolls. They come in particular sizes. They have a cost, and there's a cost to cut them. And then we have the demands for different sized final rolls, they're called. And then we have a spare threshold I'll talk about in a minute. And also these machines, some of them have a specific number of knives. You can't have more than 2 knives or 5 knives, but you'll see that in the demonstration too. So we're trying to plan how to use our current inventory of master rolls, what we need to buy outside of new master rolls, and how to cut them. And we're doing all of this with the idea to minimize our costs. So let's see the demo instead of talking about it. Let's see, here we go. First, actually, let me go back and show you how I got here. I'll go to gurobi.com. This is where you start. And you log in. So I'm already logged in as myself, but you have to be logged in there. And currently the website doesn't contain a link to these demos. I think that'll change soon. But right now you have to type in, once you're logged into the Gurobi.com, you type demos.gurobi.com, as you see in the address bar here at the top. So I've just logged in and gone to demos, and you come to this page. By default, it takes you to the cutting stock demo. That's where we are now, cut stock, and also the title over here shows it. And we're on the page that allows us to create scenarios. There are different predefined scenarios that are loaded in, but also this will eventually show a list of scenarios that you've created after you've created some. They get stored with your user login, and you have access to them indefinitely. We can also, before I get too far into this demo, let me just show you if you can switch demos. So right now we have 2. Cutting stock is the one we're on, but we could jump over to the workforce assignment demo. Okay, so let's create a scenario. This is cool. So I'm going to create a big discrepancy scenario. We call it that, and you'll see why in a moment. I'll call it Dan's demo. And I can put a description in here. And actually, that's a good idea most of the time, because you end up, it's surprising how quickly you amass a big library of scenarios. So it's good to have some descriptive information. And you see it shows up my scenario, all my scenarios. I have another one I created earlier in this drop-down list. That'll be important later, so we'll check on that. So now here's the input data we talked about. These are master rolls that are available to us. Right now we either have inventory or can purchase 50-inch wide rolls or 100-inch wide rolls. And I can edit this information. I can change the cost to whatever today's cost is. I can change my current inventory. If I discover, oh, there was a roll hidden in the back of the factory, I can change that. And then we can specify the cost for cutting. And I think in a real world application, there would be other parameters here too, but it's easy to extend this demo with your own parameters and make it your own. So that's easy to do. And then we also have information about final rolls, their widths, and the demand for them from the production floor. And I can change these values as well. And I think also these charts that you see here are useful, especially to an analyst who's familiar with the problem. he'll glance at this demand and he'll see if something's wrong. Maybe he's not used to seeing a lot of these 21-inch rolls. And if he sees a large number there, I think that visual is really important in these kinds of applications. So we're demonstrating that here with a little chart. So now we've got a bunch of data. We could add to that or delete or whatever we want, but now we're ready to optimize. Before we do, there are two other parameters. There's one called the spare threshold. And this is the maximum, or rather the minimum size of a piece of scrap that's cut from a master roll that we would keep for future use. I think 50 is a large number. As you see, it'll cost us too, but we'll leave it at that. That's the default that you get with this particular scenario that's predefined. And we can also specify the number of knives. So by default, it just assumes you can add as many knives as you need to the machine for cutting patterns. So we'll leave it at that. So I just clicked the optimize button, and what happened? There was a negotiation, which you'll see in great detail in a moment, but in the end, Gurobi Instant Cloud was used to solve this. It could be Compute Server too, by the way. But Instant Cloud solved the problem, and now we have a solution that's been returned to our web browser here. This is Firefox, but it could, no, this is Google, but it could be any web browser. We also have a job ID. If we needed to, we could go look up the job ID on the server, find out what's going on. We also have a log from the server. So some of this will be familiar to you if you know Gurobi. You can see the ranges of coefficients, other things going on in the model. Here's the MIP tree being as the MIP is solved. Anyway, so the log is there if you need it, and you can download it. But that's not what we're here for. We're here to see a solution. So here's what Gurobi figured out for us. The red area, first of all, each row of this thing is a pattern. So this pattern is a 50-inch roll, master roll. We're going to cut out a 28 and a 21-inch roll from that. And we're going to have 1 inch of scrap. But it's just a pattern, and so actually we're going to do that 3 times for this pattern. Over here on the right, there's a quantity. And then here's everything else is a 1 except this 100-inch roll down here. We're going to make 2 of those. So the optimization figured out this was the best way to minimize cost by cutting master rolls. And also over here on the right, you see there's a buying order. That's how many 100-inch rolls we're going to buy. In this case, the model decided we didn't need to buy any 50-inch rolls. So let's see some KPIs. The beauty of these kinds of user interfaces is that you can add widgets of various kinds. It's pretty easy to find predefined ones for doing things like this, for showing the results of the optimization. So you can very quickly, or the user rather, can very quickly see what's going on with their results. So these KPIs tell us that with this plan, we're going to waste 3.1% of our materials. And in this case, you can see it's all red, so that's all going to be scrapped. And there's some other KPIs here that might be useful, but that's the result for this scenario. Let's look at a variation of that now. Let's go back to scenarios. When I go to the scenarios tab at the far left, the one I just created called Dan's demo is there. I can use that now as a new template by duplicating it. Let's just try less waste. So you see it showed up in the drop-down box. We're in less waste now. The thing I don't like about that is all that waste. It seems like if we have, we need to create 15-inch rolls as small as 15-inch, which I got from here. They go as small as 15. Then why don't I make my spare threshold 15 and throw the rest away? So I'll just make that change and I'll optimize. And that's going out to the instant cloud, getting a solution, and then generating new HTML for me at this end. And we can look at our KPIs. Now, the total efficiency didn't change because we're counting both reusable spares and scrap as inefficiency. But if I look back and forth here, I'll go back to my previous demo. You can see that was all red before, and now a lot of it is orange. That's because we've kept some of that as reusable spares, so we won't waste it, hopefully. and we only have a 0.9% loss here, so that's pretty good. I like that better. But now let's play with it a bit more. And so I talked about number of knives, so let's change that. I gather, and I don't do production planning, so I don't really know, but I gather that some of those machines we're talking about have a limited number of knives. So we're going to arbitrarily say this machine has only 2. Actually, I don't want to do it the way I'm doing it. Let's make a new scenario. I'll save that one and just create a new one from it. I'll go back to this one and create a new one. 2 knives, I'll call it. Oh, right. No spaces in the name. So now I'm back there, and we can create this with only 2 knives. And I can optimize, and we can look at the solution. Oh, and look at that. There's a lot more red there. I bet you that's not a good solution. So we look at this, we have an 18% inefficiency. So I'll again use this drop down to compare. 18 versus 3.1, so that's not a good plan. So anyway, I think this demonstrates, I hope it does, that you can really learn your own systems. You can learn your own problem by playing with different scenarios. And I think it's a real, actually could be used in a real world scenario where I'm trying to do production planning. Now, the real world problems are going to be much richer, and we'll talk about that now. Before I leave the screen though, there's an important thing you might miss. I did when I first saw these demos. The lower left here, there's a help button that I can click, and it gives me an overview of the business problem that's being addressed by this particular demonstration. And each demo will have its own description here. In addition, there's a definitions page. When you're first learning the demo, these definitions can save you time. You're wondering, wait, what was a final role? What was a master role? That sort of thing. And there's a tutorial that if you want to just get your feet wet, this is a scenario you can walk through, and it's the one I just used, in fact, big discrepancy scenario. And it shows you how to use the demo. And lastly, there's a whole page on architecture that we'll talk about on the slides. I'll come back to that. And I'll also come back to this API tab in a moment. Let's look at architecture now. This is a tiered architecture, and it's intended to be a best practice. We're proposing this as a best way to architect your applications. As you'll see, the particular components we used are easily substituted with others, and we'll talk about that as we go through the architecture. But there are 6 key components here that I'll just describe, and 6 tiers really. So there's a web user interface that was running in my browser. It's based on React. I'll get fancy and use my laser pointer here so we know what we're talking about. So React is an architecture, or rather a framework for building user interfaces for the web, for a browser. It's a JavaScript architecture. I think it's now the most popular framework for doing that. Regardless, it's easily substituted with AngularJS or whatever you prefer, but React is a good one. Then there's a web application server. We're using Node.js, again, a very popular option. And simple. One of the things you'll see here is we've tried to keep things as simple as possible. So if you're trying to learn how to architect something like this or how to mimic some part of what we're doing here, the idea is that you don't have to spend a lot of time learning the particular component that we've used. So we've chosen components that are as generic and as simple as possible. So you don't spend a lot of time learning configuration files or whatever you need. This is kept simple. That's the main objective here. So anyway, we use Node.js for the application server. It can serve many multiples of clients at the same time. and it's also scalable, as you'll see. We have a scenario database for storing the changes I made to the data and create, and that's all encompassed in something we call a scenario. And that's stored currently in MongoDB. That's what we use. You could substitute another database very easily. We have a message queue. It's a kind of a glorified way of saying what this is. Redis is a really an in-memory parameter table, and it's commonly used actually for a very simple message queuing system. Once again, though, you can replace that with a really elaborate message queuing system if you wanted to. And then there are optimization workers. I think this might be the most interesting piece of this puzzle for most of us here. We're using Python for that, and we'll go into depth on that. But these are a separate layer in the architecture, and that's, I think, a really interesting aspect of it. And then finally, we're using Gurobi Instant Cloud in our demonstrations for the web. But you can easily, and in fact, there are instructions that come with the source code that say how to do this, but you can easily substitute compute server for Instant Cloud if you have a compute server license. So now, I'm going to go into a nice architectural diagram next, but I want you to understand what we see as the motivating factors in the architecture. And this is part of the key message that this presentation wants to get across. For many of you, we were sort of steeped in the modeling world where we're building models and solving problems. We're not really concerned with, and in fact, most of us have run models locally and provided the results to someone else. So we don't have a lot of experience with deploying these. And one of the things we want to get across here is to remember that optimization is compute intensive. And it's more so than most software, I think, that any of us encounters. That any kind of business software is usually less compute intensive than optimization. And so CPU is critical here. Clock speed, solve times are almost linear with clock speed. And core count is also critical for most models, especially MIPS. It's pretty unusual to see problems being solved with less than 4 cores, very unusual actually. And 8 is really typical now. Memory is less of a factor, but running out of it is very expensive performance-wise. So that's a factor to consider. And so in short, I put here that optimization doesn't share well with others because it wants its own computer, its own cores, its own memory, and it doesn't want to share it with a web server or other processes or a desktop user. It wants its own computer to do its job well. Okay, now optimization is also synchronous. This is something that we don't think about as OR practitioners usually until we start deploying an application for others to use, and it becomes a problem. Gurobi will not return from an optimize call until it's done solving. So whatever code I'm using, and this can be in a local application on my desktop, it can be a compute server, I'm talking to the compute server, I'm talking to a cloud machine way across the internet somewhere. When I call optimize in an interactive session or in my code, that blocks. It doesn't return until the optimizer is done. So this is a key factor in the architecture you're going to see. And the last point here is that Gurobi Server and Instant Cloud are really designed to maximize compute resources. So we almost take care of the first point by using them in our architecture. You'll see that. So here's the diagram. This is really the center point of the whole presentation. Now, I'm going to talk about application flow in a minute, but if you can ignore the words on the 1, 2, 3, the numbered items, just look at the diagram across the middle. Let's talk about these pieces first, and they'll come back and walk through application flow. So the pieces of this puzzle include the browser, where web clients are operating on the left. And then there are app servers, as I mentioned before, that are running Node.js, 1 or more. We default to, I think, starting 2. We'll go into more about that in a moment, but the web server is serving up the pages for the browser. It's also storing the scenarios into a database when we make changes and submitting requests when we would do so through the user interface. There's a message queue based on Redis and a database, MongoDB in this case. And then there's this thing that I think, again, that this is the most interesting part of this presentation, the optimization worker. This is written in Python, and we'll spend time talking about what it does. And then there's Instant Cloud or Compute Server if you want to switch to that, if you have your own compute server. So let's walk through this one scenario of one of the scenarios I just ran. So let's say number one is when I change the number of knives in the user interface. And when I change that, the scenario was saved by the web app server to the database. By the way, there's a connection between the app server and the web clients that uses WebSockets that makes it more of a live connection. It means that the web server can push changes to the client, and everything happens as if they're connected. Well, they are connected. It's a little different than the asynchronous sort of thing you normally get with HTTP. WebSockets makes that more interactive, makes the application more responsive. So the scenario was saved in the database. And at some point, I clicked the button to optimize. So the web server responded to that and added a message to the message queue for the optimizations. There's a queue that the workers are going to look at, but it's a queue that's saying this scenario needs to be optimized. It's waiting, and please solve it. That'll be answered by an optimization worker later. So, but meanwhile, then after it's posted that to the queue, the app server goes on watching another queue that will indicate that there's a result or a solution ready. So it's polling that queue, it's checking it to see if it's if there's a new solution ready. Now, okay, so then over here on the right, these optimization workers are already running. They're doing nothing right now, polling the original queue, the optimization queue, saying, hey, are there any jobs I should be working on? Are there any jobs I should be working on? Repeatedly looping through that. And then after we've posted to that queue, one of them gets the new request. And because it's being used as a message queue, Redis guarantees that only one of them will get that request. Redis takes care of that synchronicity. There's no problem of maybe two optimization workers picking up the same job. That won't happen thanks to Redis. So we have now an optimization worker has a request and some identifying information in that request. It'll use that information to go get the scenario from the database, load it up, and it's already got a model contained in the worker. So really, I think of an optimization worker as a model with some plumbing around it that we'll talk about in a minute, but really it's just a model. And what we've done is, Michelle Jasinski's team has done is produce these in a way that they're model specific. So there's one model per type of worker. Anyway, so there's a model there and some other stuff that allows it to read the scenario from the database, instantiate the model, and then call optimize. So every one of these workers has at least one line in it that says optimize. And then we go over to the instant cloud, and it solves a problem. The worker is still blocking at that optimize call. When the solution's done, the worker returns from the optimize call, and it can then write the solution to the database. It'll gather information from the solution and write it to the database before it ends the session with the Instant Cloud server. And then finally, that worker will push a message to this queue that indicates a job is done, a solution is ready, and that is on Redis. And then it's done. It goes back to looping and looking for a new job. So that's the entire life cycle of the optimization worker. Now we'll come back over to the lower left, and number 12, the app server then sees this new item in the solutions queue, and it gathers identifying information from it. It says, oh yeah, I know this job. This is the one I'm watching for this particular client session. So it's got a notion of what sessions are going on, so it then goes to the scenario database and loads the solution for that problem and generates web pages or web content really, and pushes them into the client. So you may have noticed when I clicked optimize, there were a lot of things going on there that were, when the optimization was taken back with the message, I didn't have to click anything or refresh the browser. That could have been done on the client side, I suppose, but it wasn't, because we use WebSockets. The app server was able to push that back to the browser, and then that's it. That's the whole cycle. It's a lot to absorb. I'll give you a minute to think about that, and then we'll go on to the key points here. So these are the things we think are the main takeaways from this. We'll show you how to do these things, but whether you use our architecture or not, the things that need attention when you're doing something like this are these three items. First, you need to separate the optimization from the web server. Whatever else you do, don't run optimizers in a web server, please, because they're CPU intensive, and the CPUs they need are very different from the web server. It'll be a blocking thing where the optimization will cause the web server to slow down, or worse, the other way around. I don't know which is worse. They're both bad. But also having them separate enables you to scale the two pieces separately. Let's go back a minute and look at that. A web server, Node.js server can serve, actually, I don't know how many. It's been a while since I've studied Node.js, but I know depending on the web app, it could potentially serve thousands of clients concurrently. I think in this case it'd be fewer because we're doing this web sockets. But still, the point is it can serve lots of clients at one time. You don't need as many of those machines for serving up the web part of this. And now, but an optimization worker, we're saying one per problem, one per solution. And that's a very different sort of thing. So we're separating those two pieces. And we're even going further in separating the optimization because it requires really hardcore CPU power. Optimization worker is building a model. It needs some power, but not like an optimization solver needs. Gurobi needs cores and CPU clock speed. And so we've separated all these pieces and really tried to draw a line between the user interface and the back end. That's the main piece here. So back to the slide I was on a moment ago, that's what we're trying to do, is split these two pieces. And so that's the first point. Separate optimization from the web server or from the user interface if you're doing a desktop. It's the same problem, really. If you're solving in the same thread on the desktop application as the user interface, that's going to hang the user interface while the optimization occurs, and it'll slow down the optimization. Right, so the next point is use an application level queue for optimization. Compute server and instant cloud provide a queue for you. So you may be asking, why do I need a queue? I've got a compute server, I've got instant cloud. Well, those are used to sequence the solving of problems so that you don't overload the machine at one time. And you really, it's good to have a separate queue in addition to that to help with the separation of the previous point, but mainly to prevent the user interface from blocking while anything else is going on. Because if I submit a job to compute server or instant cloud, the optimized call is still going to block while I'm in the queue. I can check the queue status and other things, but still that optimization call is not going to return until it solves or until I abort, cancel the solution. So we want to avoid doing that. And so an application level queue is important for these kinds of applications. And then the third thing, and this is true whether you're doing a web application or desktop or anything, is to separate the modeling from the rest of the application. Because they're really different areas of responsibility in most organizations, even if they aren't. They're different disciplines. So if I'm writing an optimization application, let's say in Java, let's say I have a nice fancy user interface running on the desktop, and I just throw the model code in there. It's a bad habit, I think. Even if I wrote the model code in Java, which you can do with Gurobi, it serves almost any API you might, or language rather, that you might want to use. Let's say I'm doing both in Java, I would still separate them. I would have the model code separate from the rest of the application, because I want to think differently when I'm working in that model code. And most commonly, it's not like that. It's a separate person doing the model code. So it's even more important to separate responsibilities. So separate those two things. Those are the 3 points. If you take away anything from this presentation, this is it. We'd like you to remember that. So now let's talk about deployment. It exposes more information about the application architecture. And I think you'd be curious. I was when I was learning how these demos worked. So we're using AWS, Amazon Web Services, for this application. But all the services we're using from Amazon are also available in similar form on other providers like Azure and Google Cloud. Any of the cloud providers will have similar services available to you. And so let's start at the gray box in the middle. So this gray box in the middle contains red boxes, each of which is a Docker container. And we've separated, I'll reiterate until you're tired of hearing it, we're separating the application servers from the optimization workers completely. But we're also separating each of the applications. We could probably combine the two demos, the workforce assignment and the cutting stock. We could combine them into one app server, but no, that's no need. That's one of the beauties of Docker. You have these very lightweight containers. You spin them up when they're needed. And another thing to think about is there maybe that the workforce assignment demo will be very popular and the other one won't. So why should we? It'd be nice to be able to scale each of those separately. And so let's talk about that. At the left, there's a thing called AWS Load Balancer. This is on the simplest form, it's just doing routing. When there's a client that requests the cutting stock demo, let's say, the URL it's requesting will be used by the load balancer to decide which application server to direct the request to. So it's doing that, it's doing routing, basically, of HTTP requests. And but in addition, when it sees a particular level of traffic on, let's say, on the cutting stock demo, when it exceeds a certain level, instead of using the two containers we create by default that are already there, when it gets to a certain level, it says, oh, I better add another app, demo one app container. And so it'll do that automatically. We don't have to think about it. We just configure it. So we, and I actually don't know what these numbers are. I assume there's a number we look at for each demo. We're saying, well, that demo gets to 10 concurrent users or 100, I don't know what it is. Then let's spin up another Docker container to support it, to support the traffic. And so, so there's a load balancer on that side that's helping and doing routing. Then on the worker side, I don't know how many we can spin up by default. I think it's 2 on those as well. Anyway, there's a set number. We don't have load balancing on over there yet, although that would probably be a good idea. But there's a fixed number of those being spun up. So what will happen is if after this presentation you all run the demos, some of you might have a slowdown because I think we cap the number of workers. I'm not sure about that. I think that's true. So there could be a wait for some of you if you all go at once. But that's okay, that'll be fun to play with. Anyway, there's another thing here that's I found very interesting, is that we're focusing each worker on a particular model. And so we could have had all the models that we're ever going to use in any of our demos and have a common worker that was available to run all of them. Well, the first complaint I would have about that is it makes the code much more complex than it needs to be, harder to maintain, harder to understand for a new programmer. And so that's a consideration. I think it's a big one here because we're trying to make this transparent and easy to understand. But in a real world production scenario, maybe that's a secondary issue. But also it lets us, again, later on, if we want to, add a load balancer and scale those based on the particular demo that's being run. And that's a very useful kind of thing. So, and now then other boxes in this picture. Up at the top, you see the Redis server, the message queue. That's just a service that AWS provides. We don't have a container. We could actually spin up our own Docker container and do all that. AWS has that figured out. We don't have to worry about it. We'll just use their service, and it's very performant. So we don't worry about it, and we use their service. It's the AWS implementation of Redis, which is an open source system. And MongoDB is very similar, although we're using a third party. It's not an Amazon product. It's MongoDB Atlas. But again, it's a service that we're subscribing to for these demos. We're using them. And if you remember, the workers and the apps both communicate with each of these two blue boxes. But so that's easy. That's in our configuration. Now, here's the real cool thing about using Docker containers for all this, is we can use another system to spin them up. So we use this product called AWS Fargate. I don't have hands-on experience with Fargate myself, so take this with a grain of salt, but I believe it's sort of analogous to Kubernetes, or it's simpler though. It's just a system for very simply spinning up Docker containers and services to produce an application. And it also includes and works with this container repository. So when I'm, as a developer, deploying my application, I can submit these Docker images to the repository and tell Fargate to update the system. That's all I have to do. I don't have to, after I've configured all of this and standardized it, I don't have to worry about how these workers get spun up, or if I've done it the same way as I did last time. It's all standardized now and programmed into this Fargate configuration. So I think it's a great way to do it. And it's important because it's not just about deployment. It's also about, it's used for development scenarios and quality assurance scenarios. So for a real production system, we've got a development scenario. Instead of testing in my own way, I'm used to doing like my own scripts and other things for doing testing a web application. That's error prone, because when it comes time to deploy the real application, I'm following a different pipeline, a different path. And so it's better to have a standardized system for doing this. So that's what we do. When I'm doing testing, I can hit a button and I know that the code that's executing is following the same path that the quality assurance, that the deployed code will follow. Same for quality assurance. So we use the same systems to do all of this. On the development side, we use a continuous integration tool, and that's really a best practice as well, although it's not emphasized here. But Jenkins is what Gurobi uses in development, and it's used to deploy these Docker images for these for AWS for doing development and for the ones that you'll use yourself. That's a lot of words for this screen. So there is another demonstration, this workforce assignment. I'll leave it as homework so that you can investigate that yourself. So you have homework. The first one is to try the cutting stock demo. For that, you'll go to gurobi.com, log in, and then enter demos.gurobi.com in the address bar to get to the web page. There's a button up here that looks like a little grid. It's a grid icon. I don't know what you call that. And it has multiple applications under it. We have 2 so far, so you can choose your application. By default, you're taken directly to the cutting stock demo though. Okay, and then there's a workforce assignment demo as well that you can check out. And now don't forget the documentation I showed you. Oh, I did skip one part, which we'll jump back to if time permits. But we also need your help. The other part of your homework, if you choose to accept it, is to help us, please, by emailing suggestions. We have a cutting stock demo and a workforce assignment demo that are pretty simple applications. And we're working on some others, but we'd like to know what is interesting to you, because we could make a very rich industry-specific demo that appeals to 1% of you, and that's okay, but it'd be better if it appealed to 10% of you. So your input is really valuable right now. We'd really appreciate anything you can tell us about that.